Well, hello. Let's do some calculus. Well, let's do some pre-calculus first. So, what we are going to do here is a preview of a pre-calculus first. So let's go and say pre-calc. Oh yeah, I spell calculus with K because I can. So yeah, deal with that. Pre-calc. There we go. And these are the things that you need to survive calculus, right? So what we need? We need the definition of a function. Entire course deals with functions. Everything is just function. So what is a function? Function is a rule which assigns to each x in the domain a unique y in the range. And important words are rule, domain, range, oops, and the word unique is misspelled. There we go. And the word unique is, there we go. So what we have here is the basic building block of our calculus course, because we will perform our calculus on functions. So you are probably seeing notation y equal f of x, where x is your input, meaning that's the domain, set of all input values. You can also say set of all possible input values to get this one, which is output, also known as range, and that's the set of output values. Now, function is a rule that changes the number from the input to a number which is the output. So you can also have a diagram for this. This is x coming in, function operates on it, and the y comes out. So if I give an example of f of x is equal to, let's say, x squared plus 6, f of 3 is 3 squared plus 6, which is 15. So the diagram for this is 3 is coming in, and then x squared plus 6 operates on it, and the 15 comes out. So that's what we have. Now we can plug in a different value, f of 0. So 0 squared plus 6 would be just 6. You can plug in a negative number, negative 4. That's going to give you negative 4 squared plus 6 is 22. 4 squared is 16, right? Negative goes away because negative times negative isn't positive. So we get 22. So you got your input, into the function and your output out of the function. So what is the function essentially doing? It is changing the numbers according to the rule that you have assigned. Now, we have a whole bunch of other functions which we are going to mention soon. Before we jump there, just want to talk a little bit about this uniqueness business over here. This is the word that makes the function, which is why I underlined that one twice. Right? So you know the rule is the formula, domain is the set of input values, range is the set of output values. You know all of that. Unique, word unique, is there to make sure that you understand that 1x produces 1y. That's the deal. So you can have multiple x's produce the same y, that's okay, but you cannot have 1x to give two different y's. That is not allowed. So we can put that also in a diagram. We can say that you have your set of input. Let's use domain and range. Domain and range, and then you can have these values that map into x1, x2, x3 that map here. And as you can see, I'll put this okay, right? Because 1x producing a single y, that's good. You can see that on a linear graph, or you can see that pretty much on any function graph. So a single x value goes up and produces a single y value. And then this point here is x1, x2. Oh, sorry, x1, y1. You can also see the second part where two different x's produce the same y value. That's going to be your x squared graph. That's a function as well. We see this x and this x. So x2 and x3 are producing the same y2. So that's the second part of that. So all of these are functions, and you can test if expression is a function by using vertical line test. So vertical line test. Give me just a second. I gotta change the battery in the pen. I'll be right back. So we'll Are we all good now? Test, test, test. You still there? Say something in chat. Say, we're all here. Okay. Thank you, Franco. Right. So, vertical line test. will tell us if that vertical line test will tell us whether we have a function or just what we call a relation. Vertical line test, so all vertical lines can cut through function creating single y-intercept. So if I draw, as you can see over here, as many of these vertical lines as I want, each one cuts through the graph only once, creating a single y-intercept. Same happens here. No matter where I draw a vertical line, those are not vertical, but let's say they are, they all cut through the function only once. So something is a function if it passes vertical line test, meaning that the function is cut exactly once by these lines. Now, what happens if you have something that it's not a function? For instance, a circle or ellipse in this case. Actually, hold on. I practice drawing circles. I can do a perfect job. Spent years practicing this, so see, my circles are the best. All right, so here is a circle, and this circle has, you know, the radius and all that stuff. We can center this circle at the origin if we want to. It doesn't really matter. Call this, I don't know, 5. So equation for this is x squared plus y squared equals 25. This equation was in intermediate algebra, for instance. So now, when you look at this circle, when I draw the vertical line, look what happens. It cuts through the line twice, right? Cuts through circle twice, here and here, producing 2 y values. And that's no bueno for a function. So, single x producing 2 y's, not good. So this is not a function. There are many examples of this, and you can generally spot them when you see y squared, because y squared will square root both sides and put the plus and minus, and that's how you get the 2 values, one positive, one negative. So, so that's the basic of a function. Being able to figure out domain will be helpful, because especially chapter 4, when you want to learn to graph a function by hand. Why are we graphing functions by hand? Well, it does have some benefits, even though we have the technology to do all of that stuff for us very quickly. Universities are still not allowing any type of a calculator. The more graphing you learn in Kalk1, the easier will be to go through some of the coursework later on. Math courses at NGIT and Rutgers and Virginia Tech and so on, they don't allow calculators at all of any kind, not even basic ones. So the more you learn about computation and functions in terms of graphing now, easier it is later on. So it's good to know domain because you know not to focus outside of the values that are possible for graphs. So we'll talk about the domain as we are reviewing the basic graphs. So basic graphs and the domain. That's what we are going to look at now. So function y equals a c, known as a constant function. So constant function. That's, let's say, y equals to 3. So you will just have a straight line at 3. You can see it's horizontal line, right? It's constant. It doesn't change the y value. That's why it's called a constant function. It's always 3. And the domain will be all real numbers. So we can do that, or we can do this, right? From negative infinity to infinity. So domain is the set of all input values. And you can see that x can be anything, right? X is not even in a formula. That's how loose x is in this case. The next creature is y equal mx plus b. That's your linear line, linear function, also studied in algebra. And this introduces the slope m and all of that kind of stuff. So you can have an example of something, let's say, like this. And in this case, domain is again all real numbers. This R has 2 bars as we draw this, and you just put your x and your y, and you're done. So that was a linear function. Then y equal ax squared plus bx plus c. That's the quadratic function. And that's the u-shaped one. We already talked about it. It doesn't have to go through 0, 0. Right? X squared goes through 0, 0, but x squared plus 1 goes through 1. So all of that stuff is important. Domain is again all real numbers. So that's cool. And instead of going x cubed, x to the 4th, x to the 5th, I'm just going to say y equals x to the p. So polynomial function. And all of those above, quadratic, linear, and constant, are parts of a polynomial function. Polynomial function p of x is given as a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 plus an x to the n. You can go with this exponent as high as you want. I've never seen it, but if you want x to the 17 in your application, you can have that for sure. Generally, for applications in terms of physics and engineering, you can go up to cube, maybe 4th, maybe, but that's it. That's it. The nature is really basic and simple. Those of you who studied pre-calc at RVCC, you are already recognizing your chapter 2 from pre-calc 2, where you learn the polynomials and leading coefficient test and all of that stuff to graph the functions and find zeros. So all of that stuff fits now. The entire chapter 2 fits on the screen. After polynomial functions, we are going to take a look at the radical function. And this is the first time where the domain gets to be different. So domain is including 0 and then going to positive infinity. Actually, I should have. Let me redo this because I forgot to put a graph. I'll put the graph here. There we go. So that's our graph. And we can just go here and say x larger or equal than 0. You can only take a square root of positive numbers if you want a real answer. Taking square root of negative numbers, you are going to get a complex answer, right? Imaginary. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is about 1.4, and so on. So you can take these roots. You can use the calculator to get the roots, And what you need to know is that you can, if you are looking for a real answer, then your input has to be non-negative number. And I say non-negative because 0, you can take a square root of 0. 0 is non-negative. 0 is not positive. So you can't just say positive numbers. You say non-negative, so you can include 0 in the set. Or you can say positive numbers and 0. That's another way. So that will be the square root. Then we have y equal 1 over x. That's rational. We'll see a fair share of rational functions as well in this course. 1 over x is the cheapest one to graph. Those of you who have flashbacks of pre-Kalk 1, you should be having flashbacks of 2.6 at this point, where you graphed the oblique and did those asymptotes, which we are going to redefine, maybe even today. So yeah, all of that cool stuff. Domain, you're not allowed to have 0 in the denominator, right? So x cannot be 0. So what's the domain? Domain is everything except 0. And you can get that by saying negative infinity to 0. Then you break with the parentheses and the union symbol. Right? The U in between means union. And you have two parts, right, that are united to create the domain. So are you able to plug in negative 2? Sure, you get negative 1/2. See? Negative 2 gives you negative 1/2. Does it make sense? Sure, when you replace this number with the negative 2, you get negative 1 over 2. So, negative numbers are okay, as long, right, as it's not 0, domain, we can compute values for rational function. And now we go with our exponential function, y equal b to the x. Now, you might used already, right? You gotten used to using e. Well, e is a special number. It's a constant number, right? About 2.7. So that's a special base. But you can have 2 to the x, you can have 3 to the x, you can have 10 to the x. And all of those look the same. They just grow faster if they have a larger number in the base. We don't generally, stress too much about drawing these because it's not humanly possible to do an amazing job at exponential function, as long as you know it's something like this where it goes sluggishly, right? And then it just shoots up real fast, so we can call it exponential growth, right? So the one that you probably remember the best is e to the x, and that's the one that we are actually going to use all the time, e to the x. It drives most of the calculus. Domain, as you can see, all real numbers again, because you are allowed to plug in any x value you want, including 0, e to the 0 is 1, or 3 to the 0 is 1. So this value over here is 1 on the basic graph. That leaves us with y equal ln of x. And that's the, well, actually let's do the log base a of x, logarithmic function. You are used to ln x because base is e. We'll have a whole spiel on this once we get to logarithmic differentiation. So I know that some of you are not good with logs because it was an operation that was not introduced until pre-calculus. We are going to have logarithmic differentiation, and logs will be the part of many sections. When we need logs and details and the formulas of logs, I'm going to put that in the lecture, right? Right now, it's enough to know that y equals ln x is actually log base e of x. Domain, when you take a look at the picture over here, is only positive numbers, so not including 0. That's why we can say positive numbers. We are not including 0 in this case. And logs tend to do this. Cool. One more, which I want to present, and then we are going to take a look at the shifting of the graphs, is the absolute value. So y equal absolute value of f of x. Now, you guys are used to absolute value of x. So y equal absolute value of x. And you know probably that it's a V shape, right? So yeah, that's all great, but what is the absolute value of sine x, right? So when you think about this, you have a function. So absolute value makes all negative values positive values, right? I can't draw at an angle over here the way I have to rearrange my desk, I guess. There we go. Now I'm going to draw a function and then erase a piece. There we go. So this is your function y equal x. Now, here is this piece that stays the same, and the other one gets reflected up because it's below x-axis where the negative y values are. Remember, the answer, right, that you get out of the absolute value are always positive values. So all y's need to be positive. So for absolute value graphs, as long as you have anything under the absolute value graph, it will jump up. And whatever was above x-axis will stay where it is. So let's say y equals 1 over x. So 1 over x, we set graphs this way. Now, if I want to put the absolute value on that, then this one stays where it is, and this one jumps up. Does this, I hope this makes sense. So, when you have absolute value of any function, whatever is under the x-axis will, like in a mirror, just jump up, reflect up, and that's it. So now we go and we take a look at trig functions. We have 6 of those. Then we have 6 inverse trigonometric functions, so there are 12. 12 trig functions that we are not going to use all of them. Sine, cosine, tangent, secant, inverse tangent, inverse sine, those are the important ones. The rest pretty much don't show up almost at all. So trig, we have y equal sine x, and the one period of that would look like this, ending at 2 pi. Trigonometric functions are different than all previous functions for the reason that they repeat. So think about an event which happened only once in your life. So think of some kind of event. I don't know. It doesn't really matter. You won in a game, right? I was born. Okay, good. That perfect example. Thank you. I was born. So, um, so we have that event that happened only once, and that's it. Now think about weeks. Weeks repeat, right? After Monday, you have Tuesday, and then Wednesday, and so on. Then Sunday, and then Monday again. Tuesday, Wednesday, blah blah blah. Then you get to Sunday, Monday again, and so on, right? So it's periodic, and it goes for a long, long time. So that's what the trig functions actually do. They repeat. And when we draw only one period, like I did, we are not representing all of the trig function. We are representing one piece, and we know that that one piece will forever repeat in the same way to the left and to the right. So domain for these functions is negative infinity to positive infinity, but the principal period here is 0 to 2 pi, because that's only one instance of the function. So you can take a look at a week, right? You can take a look at the week, and then that's only 1 week. You know that after that there's going to be another week, and there was a week before that week. But you are only looking at that 1 week at the moment, right? So for trig functions, you need to pick up from the context. Usually problem gives you the domain if they want you to focus on a single period, or they say draw 2 periods or something. That's all okay. But in terms of the function itself, it has infinite domain. So the cosine does the same thing, except is shifted. So the cosine is going to start on top, dip down, go up, and end at 2 pi. Tangent x is going to be like a cubic function, centered at 0, go through, and go up. And that's from negative pi over 2 to pi, so its period is pi. So from negative pi over 2 to positive pi over 2, that means half of pi on each side. Together it's a 1 pi for the period. And then we have the other 3 functions. Now you will find that secant is used a lot in calculus. Not just Kalk1, Kalk2 and Kalk3. So secant is going to be used as much as sine and cosine and tangent. That function is insanely important. Now, cosecant and cotangent are barely seen. You are going to run into them, a couple of times in each calculus, but they are never focus of anything, because they are technically just the shifts of secant tangent thing. So we don't really need to focus on them, because we can deal with all of the applications using secant and tangent. Now, how do we get those, and what are those graphs? So, depending on how people teach those, when I teach pre-calc, I make it easy this way. To find cosecant, which is 1 over sine, you will draw sine, right? And I'm going to do this dotted line here, because I'm trying to graph a cosecant, not sine. And everywhere where sine hits x-axis, we are going to put the vertical asymptote. remember, cosecant x is 1 divided by sine. So when sine is 0, you have infinity. That's why you have asymptote there. And since this is a flip, all I need to do now is to take the scissors and cut down this line and invert these. There you go. So that's your cosecant. That's how simple it is. Anytime you need to graph cosecant, graph the sine function and just flip it out. Do the same for cosine, which is secant, and cotangent, which was a flip of tangent. So if I want to graph the secant graph, we are going to start with the cosine. Hold on. Anywhere the cosine hits 0, put the asymptote, and now flip it out. This is your secant x graph. And the tangent will flip as well to get the cotangent. So this guy is going to actually have an asymptote at the end, and it's going to be a flip through pi over 2. So tangent goes through 0. Right? Tangent goes to 0, and the cotangent x goes through pi over 2. And it's flipped. You see that it starts up and go down, where the tangent started down and went up. So those are the trig ones. A couple of formulas that will be beneficial. Tangent x is sine x over cosine x. Cotangent x is cosine x over sine x. Secant x is 1 over cosine x, and cosecant x is 1 over sine x. It will be useful to set up a triangle. This is the adjacent side because it's touching the angle. This is the opposite leg, opposite side, because it's not touching the angle. And this is the hypotenuse, the longest side in the triangle. And with this we can set up all 6 trigonometric functions. So if you have distances and angles and so on, you can actually create functions. This will be insanely useful later on for engineering, physics, and so on. So sine theta is opposite over adjacent. No, lies, hypotenuse. There we go. Cosine theta is adjacent over hypotenuse. And tangent theta is opposite over adjacent. Then you know that the cosecant is 1 over sine. So if cosecant is 1 over sine, that must be hypotenuse over opposite. Secant 1 over cosine has to be hypotenuse over adjacent. And cotangent theta must be adjacent over opposite. This will be mainly used to set up your word problems in chapter 3 and chapter 4. So then you are going to use it in Kalk1 for trigonometric substitution, and you're going to use it in chapter 12 again in Kalk1, so on. So there will be a lot of use for these things. So that's what we have for for this. Now, what else? Let's see. The rest of the formulas and graphs, we can do some shifting. We can do shift up and shift down. Left and right. Yes, this was, I just read in a chat, SOHCAHTOA. Yes, this is used as SOHCAHTOA. I usually actually have to copy it. Oh, sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, and tangent. Like, these things are hard for me to remember because I already know these things, and then I have to actually work it out. But great, if you know this, use it. You will need it to set up the problems. All right. Shift graphs. So if you have a function and you add or subtract the value, positive will move it up, negative will move it down. Example of that is y equals square root of x, which is normal graph starting at 0, 0, and you say root x, and then you say plus 2. So plus 2 is going to move it up at 2. Keep the same shape of the graph, keep everything the same, it's just going up 2 units. You can also shift the functions left and right. So that will be done directly on x. So plus will move it left, and minus will move it right. So y equal root x will be still the same graph we know. And then you go y equals square root of x minus 2. Let's do plus 2. So you can compare it with the other shift. And the plus moves it to the left. So you will go 1, 2 units. And you will have your graph there. So these are shifts. Now there are also stretches and shrinks and so on. Not so much important. Reflections are important. When you have negative f of x, right? And when you have f of minus x. So these are the two reflections that that you can have, right? Two reflections. So negative f of x is going to reflect, you can see that the whole function becomes negative, right? So all of your y's become negative y's. So that's a reflection on x-axis. So if you have your y equals square root of x, which looks like this, and then you have y equal negative root x, in that case, it will just drop below x-axis like this. So that's our reflection. And then this one is a reflection on y. So y equals square root of x, and then y equals square root of negative x. So we still have our original function looking like that. And now the function is reflected, so it looks like this. Now, before you say, but professor, you said we can't have a negative under the root. You don't. You still have a positive value under the root. Because look what values you are allowed to plug in for x. Negatives, right? And then the negative over here will give you a positive number. So if you pick negative 4, and when you plug that in, you will get y equals square root of negative 4, which is square root of 4, which is 2. So we're all good to go. So it's still giving you a positive value under the radical. Right? That's it. So are we still good with review? Any questions so far? Okay, so those were the reflections and so on. The reflections can be combined. So remember how I mentioned the exponential decay function, right? So if I have y equals e to the negative x plus 2, this one has two transformations. There is a transformation here. Remember, that's your negative x transformation. That's a reflection on y-axis. So y-axis reflection, and this is shift up 2 units. So you can do this in 3 stages. You start with your original function e to the x. Then you reflect that on y-axis to make it to be e to the negative x. That's the decay. And then you shift everything 2 units up to make it fit the last requirement. So this was 1, now 2, and it's going to go through 3 now. And your horizontal asymptote that you have for exponential function shifts up. Shifts up 2 units as well. That was bad. It was terrible. It's here. That's where it shifts. And you're going to have the decay function go like this now. And this is your e to the negative x plus 2. So every point of the graph went 2 units up, right? And it was reflected because of negative x. Yes, these are the basic functions, and then you keep shifting and switching them around as you need. So yes, the list of on the top are the prime functions, the basic functions, default functions, whatever. So these are the ones that are studied in pre-calc. As I said, it's not even scratching the surface of what's out there, but these are enough for us to go through calculus. And once you learn the calculus, you will be fine. Now, the one thing that you need to know now for calculus is this stuff now, calculus operates on functions, right? So you are going to take a limit of a function. You are going to take derivative of the function. You're going to integrate the function. So functions operate and deal with numbers. Calculus operates and deals with functions. So it's a higher creature, right, than a function, because it operates on a function. And you have to be very careful with your complaints to me over here, because one thing that you need to understand is that I cannot do all of the examples for all of the functions. You are learning calculus concept of what that concept does to a function. And I'm going to do 2 or 3 examples. But I cannot do all of the examples under the sun for every single function that exists. So this is the part where you have to learn concepts and then say, okay, I have exponential function. In class, we had trigonometric and a polynomial function, for instance. So these are the things that you have to be a little bit careful about as you are going into calculus. All right, now, combinations of functions. This is a biggie. Maybe I should write this in blood. It's important. So, functions give you a number, right? So remember how we plugged in whatever value and we got, I believe, 13 or whatever? So, y value at the end is a number. And you can add numbers. You can subtract numbers, multiply functions, right? So, we're going to add functions and subtract functions and multiply functions because essentially we are adding and dividing and multiplying the numbers that are in those functions. So we can do all of the operations with functions. And then more. We'll see what more is. So if I have f of x equals x squared plus 2, and let's say g of x equals to, I don't know, 1 over x. So question is, what is f plus g equal to? So you will clearly say, well, it's x squared plus 2 plus 1 over x. And you're correct. That's all it is. Now, think about it a little bit, and you will see that if you are to plug in a number into these two functions, compute and add, and if you are to plug in a number into already algebraically combined function, you will get the same value. How much is f of 1? Well, that's 1 squared plus 2, which is 3. And g of 1 is 1 over 1, which is 1. And how much is f plus g of 1? Well, it's 1 squared plus 2 plus 1 over 1, which is 4. But if you add these guys, you also get 4. So we achieve the same. Whether we add, right, we compute individual functions and then we combine them, or we algebraically combine the functions and then we compute. Let's take a look if I multiply these functions, what happens. So let's say I want to now compute f times g. Well, f times g is 1 over x times x squared plus 2, which simplifies down to x plus 2 over x. So how much is f of 1? Well, we know that's 3. How much is f of 1, g of 1? G of 1 is 1. So in this case, 3 times 1 is 3. Well, I better get 3 from here. So how much is f times g of 1? It is x, and x was 1, plus 2 over 1 is 3. There we go. Right? It has to come out to be the same. So adding, subtracting, multiplying functions, squaring a function, square rooting a function, doing all of these operations on functions behaves the same way as operating on numbers, because function f of x is equal to a y, and y is a number. So we can do with functions everything we do with numbers. So you can square a function, divide functions as long as the denominator is not 0, and do all of those good things. Well, there is one more piece, one very important piece, and that important piece is function composition. Now, this thing will be with you throughout your calculus education, and as one of the most important ways to combine functions. It's mostly used, and we have special derivative and integration techniques for it, and also because it's so important and so useful later on. So now, if I could have double red, I would do it. Function composition. Known as f of g of x, when you plug g of x into each x of f of x. So we are going to have chain rule, U substitution, integration by parts in Kalk2 later on, and so on. There will be multidimensional chain rules in Calculus 3, multivariable multidimensional chain rules, right, in Calc 3. This concept drives most of your calculus education, what you see right now on the screen. And this is combination of functions. So you create new function from other functions, and the new function doesn't have to have anything similar like the old function, could have a different domain and whole bunch of things. So the best explanation here obviously would be an example. So let's say your f of x is x squared plus square root of x, and your g of x is sine x. You have two functions. You have a function f of x, which is a combination of a polynomial and a radical function, and you have a trig function in g of x. So what do? You are supposed to, for f composed with g of x, you are supposed to plug g into f. So it would be g squared plus root of g. And what's your g? It's sine x. That's all it is. You can also do this backwards. You can have g composed with f. This is a little circle. It's not O, it's not a dot, it's a little circle. And that's g is the boss and f of x is plugged in. So g is the boss, that means sine of f. And what's f? Well, f is this x squared plus root x. So function composition is the way to plug all of these functions one into another, and it can change domain and range. You see, function f consists of two functions, polynomial function and the radical function. Remember that you can't use negatives, right? So the entire domain of the function f of x is now including 0, 0 to infinity. That's the domain of that function. And the domain of the function for sine is all real numbers. Now, when you take a look at these single functions, or composed functions, the domain over here is all real numbers. Because you can plug in any value you want into sine x. As long as the sine x is larger than 0, between 0 and 1, it can fit into the square root. Actually, no. Domain over here is sine x larger or equal than 0. That's the domain. And you can find the domain of when that is happening, right? For what values of sine? That's 0 to pi. So 0 to pi. So that's the domain of this function. It's restricted by this term. You are allowed to have sign to be positive. You are allowed for sign to be positive. Sign to be, in order for sign to be positive, that happens on that first bump because it's above the x-axis, right? This one is negative, so we throw that out. And it's the top part, 0 to pi, that gives you positive y values. Because when the sign gives out the positive value, you can compute the root. When it gives you the negative value, you can't compute the root. So that's why we can only plug in 0 to pi. Now you will say, but over here, you know, I can plug in anything because I can square it. Why does this one spoil fun for everyone else? Well, that's how it goes, right? You only need one idiot to spoil the fun for everyone else. That's how it goes in life. So it's reflected in mathematics as well, right? So when you have this expression here that has multiple terms, the one that it's most restrictive, right? One that it's most restrictive is the one that will impose the domain for everything else. So can you use number 2 as a domain here as a value? No, because sine of 2 is going to give a negative number. When you plug in that negative under the root, the whole function becomes imaginary and it's out. Now the bottom part has again root x, which is the same, 0 to infinity. So we are stuck on the same domain of 0 to infinity for the bottom. Those of you who do not remember these parentheses in the notation, I'm going to give that definition over here real quick. Include endpoints, and this one exclude endpoints. Right? We have on the bottom one. You use that for infinities because you cannot include infinity, right? The infinity is ever growing, right? So that's that part. So function composition will be used a lot, and the hope is that you will be able to quickly recognize which function plugs into which looking at the notation. So f composed with g or g composed with f. So this is your guide where it says that g is plugged into f and f is plugged into a g. I think this should do it in terms of the prerequisite knowledge. I mean, equation for the circle, area of the square, area of the rectangle, area of the circle, circumference of the circle, area of the triangle. So all of those basic areas, and so they pop up in word problems here and there. You are not failing the course if you don't know those, but you definitely are not also scoring an A in a course if you don't know it. So reviewing those basic areas, and then area formulas, as I said, only square, rectangle, circle, triangle, trapezoid, for instance, like 5 shapes, right? We are not dealing with 3D in this course. You will have a little bit of 3D in Kalk 2, and Kalk 3 is only 3D. So those of you going to Kalk 3 will also have a lot of stuff. There will be one section that will use volume, but I will teach that in literally 2 minutes, and you will be gods of volume formulas at that point. It only takes 2 minutes to learn that. So we don't have to worry until end of chapter 3, so we can relax, but you know, you might then end up looking into some areas or something before that, so you might want to know it. I think that's it. I mean, that's what we are going to cover as our intro, and more specific, you know, formulas on on exponential, log, and trig when we need them in the lecture or a problem. I will go over those from scratch every time, but as I said, this is the time to catch up and to learn it, because winter is coming, meaning Kalk2, right, is coming up, and you definitely want to know that stuff going there, because looking for the reference all the way into pre-Kalk1 when you're taking Kalk2 class, you know, three courses away becomes very hard. So let's go and deal with chapter 2 now. We're going to take a break, and once we come back, let's say at 10:05, 10:05, 10:10, 10:10. Okay, 10:10. Fine. So when we come back at 10:10, we are going to start chapter 2, and we're going to actually skip 2.1 because 2.1 will be covered in 3.1 as a part of it. It's a little bit misplaced, so we don't have to worry about 2.1 for now. We're going to go to 2.2. Our goal is 2.2, 2.3, and 2.4. Two of those are very short, and one is on the longer side, so we have plenty of time. So, oh, you want to be back? I was hoping to travel back in time. Yes, I don't even know what time it is. Yes, I traveled to the past. Good. Back to the future. I'll see you at 11:10. 11:10 for chapter 2. We are starting calculus. We are starting limits. I'm ending this stream so that this lecture saves and get posted under the title, and then I have to shut off the stream so I can change the title and restart the stream for the new lecture so the new title catches on and sorts it out. So just make sure you are back on the channel, and then you to start the new one. I'll see you all at 11:10.